maybe Ariel, are you the one who introduced our speaker today?
Yes, I will. All
Yeah.
right. So
All
good
right.
afternoon, everyone. We'll get started. I am Eleanor Heaney, a graduate student at UTK, and I'll be introducing our speaker today. Dr. Abhishek Dubey is an assistant professor of electrical engineering and computer science at Vanderbilt University and senior research scientist at the Institute for Software Integrated Systems. He directs the SCOPE lab at the Institute of Software Integrated Systems and is the co-lead of Vanderbilt Initiative for Smart Cities Operation and Research. His broad research interests are in the design and operation of decision procedures for smart and connected communities with a focus on transportation and energy networks. In particular, he focuses on design and operation of cyber-physical systems with AI-based components with a focus on public transit systems, emergency response systems, and the power grid. For these systems, his lab investigates principal design, operation, and optimization methods that not only consider the system operations, but also consider resilience, performance, and assurance. Some of his key research results include the design of hierarchical decision procedures for responding to motor vehicle crashes, the design of energy-efficient transit operation procedures, and the design of transactive energy systems. His recent publications can be obtained from his lab's publication page, which is linked on the CURENT website. And his work has been funded by NSF, NASA, DOE, ARPA-E, AFRIL, DARPA, Siemens, Cisco, and IBM. Dr. Dubey completed his PhD in electrical engineering from Vanderbilt University in 2009, his master's in electrical engineering also from Vanderbilt in August 2005, and completed his undergraduate studies in electrical engineering at the Indian Institute of Technology, Banaras Hindu University, India in May 2001. We want to thank Dr. Dubey for coming and speaking and everyone for attending. And so now I'll pass things off. Thank you.
Eleanor, I just want to quickly check. Can you see a full screen of PowerPoint? Okay. And can you hear me properly? Do I need to speak louder or lower?
Sounds good.
Okay. So thank you, Eleanor. Thank you, Chinfei, for inviting me. I know about your work at CURENT, and it's very much related to the things that we do at Vanderbilt University and ISIS. Today, I'm going to talk to all of you with some of the work that we have been doing with public transit agencies, in particular in Chattanooga, right? This work is actually, a lot of this information is available on a website that is linked below. So if you go to smarttransit.ai, you will actually find this work, lots of other information, and actually the whole team. There's a pretty big team we work with. We work with Cornell University. We have partners from University of Houston. We have partners from Pacific Northwest Lab. We have partners from Siemens Corporation. And we have partners from University of Tennessee at Chattanooga. And of course, we have partners from Vanderbilt and CARTA itself. CARTA is the transportation agency in Chattanooga. During this talk, if you have any questions, I think you can raise your hand through Zoom, and I will stop and I will answer, right? Just to try to understand what public transit agencies go through. Almost all of you had probably seen and used public transit agencies at some time in your life. You have seen the bus transportation. You've probably used it. Like at Vanderbilt, we can actually ride the Nashville bus for free. Not really for free. Vanderbilt pays the cost, but we can take our ID card and we can swap. We can show to the driver and scan, and we can then ride without paying the fare. So these agencies are really crucial for providing the connectivity throughout the surface transportation network. So you can imagine that the whole number of people are actually moving through the town. And why they are very important is because the number of people that they are shuttling, they're moving between grocery stores to the healthcare locations, to their jobs, to their friends' place, to the public events that are occurring. if they were not supporting that, those trips will be then made by single person vehicles in most cases. And you can then imagine the problems with that. That will lead to congestion, extra congestion, that will lead to extra energy being used, right? So public transit agencies perform a very important work. Now, there is a problem, right? Public transit agency, like any other agency in a city, works under fixed budget, right? There is some restrictions. They don't have an infinite amount of money. So then question starts to come, how do you run the service, right? And by the way, these questions were there 20 years ago, even 30 years ago. How do you design a bus line? What should be the frequency of the bus line? Which routes should it go visit, right? Where should the stops be located, right? So these questions are typically answered by people who are looking at the transportation planning. Now, these questions were always there. Where we come in last 6 to 7 years, we have started actually asking a slightly augmented question. So a question that goes beyond this basic question of where the bus stops are, where the routes are. We have been asking this question, that if the transit agencies in the mass transportation is really one of the major modes of moving people around, can it be more efficient than what it is today? Now, that's a very big thing to do, because if you can move that, you can almost make a dent around 15 to 20% of the transportation energy costs, right? And one of the most simplest ways that you can do this is, let's try to convert all of the diesel buses, which is like 95, 2000 time frame buses in the city centers, to electric vehicles. So you can actually run BYDs, you can run other electric, Ford electric. Now, the problem that always comes is that electric vehicles are very efficient, and they will actually provide a very nice way of transportation. They look very clean and they're environmentally friendly, but these things are expensive, right? Electric vehicles are not very cheap. So there is, again, it goes back to the fundamental problem that there is a budget, right? So you only have limited capacity to buy electric vehicles, and electric vehicles are being added slowly and slowly. Now, as the electric vehicles are being added, you also need to understand that if these electric vehicles of a city like LA, if they start to charge at the same time, you have suddenly increased the load on your electric grid as well. So since you all are in the CURENT Institute, you understand that the impact of the stability of electric grid is actually very important. If you don't plan this well, this could lead to issues. So this leads to very, very basic, nice problems for us to deal with as electric engineers and computer scientists. So, and the problems becomes this. If you have a fixed number of electric vehicles, electric buses that you can bring into your fleet, right? Which of the routes and trips should these electric vehicles be run on? Because that will decide when these electric vehicles will charge, right? That will decide the impact on the grid. And the other question that is look, if all of these buses that I'm showing to you here are electric vehicles, great, everything is efficient, but remember, you can't afford it. So the question is, where will you get the most bang for the buck to run the electric vehicle on which trips, rather than not running them, right? Because then this becomes a system-wide holistic optimization. Now, those are the questions that we are actually asking with our transit agency partners. So that's kind of the context behind the project. So let's talk, how do we do these things, right? So basically, in order to do this, we need a number of information. So first of all, you really need to look at it as something which we call CyberPhysical System. And what that means is you need to develop eyes on the problem, sensors. So just as if you think of power grid, electric grid, there is number of information coming from all the relays. You're getting complete information from new phasor measurement units. You're trying to get data because you cannot make decisions without the data. So what kind of data do you really need? One of the things that we need to know is, what are the ridership patterns? How many people use the bus line? Where do people use the bus line? right? Because then when we start actually allocating electric vehicle to a certain route, we need to probably do it where the capacity of the electric vehicle, it could run the trip length. It will have a number of stops based on how many people are going to use the service. So you need to estimate that. Now you can just imagine this. This is a very dynamic thing. You can collect past data as people are boarding the buses. You can collect how many of them are there, and then you have to predict. Now, what is the simplest way to actually understand how many people are in the bus? Every bus actually has a security camera, by the way. In almost all the cities, they do that. And this camera is actually being streaming videos in real time. So if you actually have a computer vision algorithm, you can start counting the number of people automatically. So now imagine there's a neural network, AI, that can count the number of people, and it's providing you this streaming information. So that becomes a sensor. The second thing that you can do is actually start measuring what is the energy usage, the telemetry of the vehicle. As the vehicle is moving on the line, what is its voltage, what is its speed, how much energy did it use between one point and another point. Now we have to actually collect all of this data. Now this becomes big data really very, very quickly when you start doing this across all the fleet, right? On top of that, then we can actually do this optimization where we can try to understand which bus route should have what kind of buses. Now, one of the major things we need to do for this is we need to start estimating the energy usage of the bus before it is actually finishing the trip, right? This is a dynamic estimation problem. We need to say, okay, if I put an electric bus on route 1, or if I put a diesel one on route 2, at a 5 p.m. time, what will be the energy consumption? How much fuel will it use? And this is not as simple as just looking at the fuel meter. You need to do it at a level that is much more dynamic. You need to understand as the weather is changing, as the traffic patterns is changing, as more people are boarding the vehicle, what's the usage, how much energy will be used. By the way, before we started, these kind of detailed models didn't exist. So one of the things that we have already shown to Department of Energy is that, hey, we can build these models, and we have actually shared the models with them. But these models are very fine-tuned for a city because these are data-driven models. So there is a procedure. So if we go to a different city, we can repeat the procedure again to try to train these models. And I will show you some of these models. Once you can actually estimate the energy usage, now you can think that this is an optimization problem, because if you had 4 possibilities of assigning vehicles to routes, you can enumerate all the possibilities, estimate the energy, sum it up across all the possibilities, and choose the one that has the minimum energy usage. But this becomes very quickly a combinatorial problem, because the number of bus routes are a lot and the number of buses are a lot, and when you multiply it, the choices are a lot. So it's a hard problem to solve. So then you need to, in computer science, we do things called heuristics, and then we can apply that a little bit more clever way of solving something. And basically the way, it's a nice way of saying, let me guess a very elegant new solution. And that's what we do. That's what our optimization steps is. So let's jump into this a little bit more and try to actually explain to you all the different aspects that are there, right? I will share my slides with the team. And in these slides, I've actually put on some papers at the beginning or towards the end. So if you are interested, you can actually, I'd get this paper from our website and read more and just ask questions. You can reach back to me if you have things. So the first thing that happens is basically the sensors, okay? So we worked with CARTA, and this could be done with all the buses. There are sensors that goes directly into the CAN bus of the vehicle, directly into the engine with J1939. We worked with a company called Vericity. This company has now been bought by ChargePoint. And through this company, you can actually get lots and lots of data on every telemetry from the bus. So for example, we get the bus speed, we get the brake position, the accelerator position, the fuel level, the charge rate. And you can imagine we are getting this once every 10 milliseconds, okay? 100 times a second, we are getting this value. So as the bus is moving forward, we are continuously collecting this. And now this is nothing else but just observing from every bus that is on the city line. In addition to this, We actually get a lot of data from a company called Dark Sky and another company that we have started to use called Weatherbit that just tells us what is the weather right now. Every 5 minutes, what is the wind speed across the city on different roads. You know, there are multiple weather stations in a city. It's a very fine grade information. We have actually data from 2010 up to now, and this data is going forward. Just what the temperature is, what's the humidity, how much snowfall has happened in the last 24 hours. Is it snowing currently? All that information comes in. We also work with companies that provide us real-time traffic speed data. So how fast the traffic is moving at every road segment of the city. We actually use OpenStreetMaps. So we map all the data back to OpenStreetMap segment. So route by route, road by road, we know how long it takes, what is the travel time. And this is updating every 5 minutes. So our current data go for traffic and the veracity goes for last 3 years. So you can imagine the level of data that we have now, that we have just collected, right? It's in multiple terabytes. And then we do some big data operations to join and do some GIS operations. So we can precisely identify when a bus goes from point A to point B in the city, how much energy was used. Did the driver press the brake a lot of times? How many times did it stop? What was its speed? Everything, all that information is there. What was the weather at that time? What was the traffic speed? Now, on top of that, we actually went to the Tennessee GIS and we downloaded the LiDAR data. So now we know the elevation of the city, everything on that road, right? So now you can imagine all of this is there. So now you can start learning some models, okay? This is what we call the data journey. Now this itself was a pretty difficult part and it required us to create some new cloud computing architectures. A little bit more in detail is in the paper if you want. Now with that, we also then started looking at just the occupancy, like how much the occupancy patterns are changing. Every bus, we have a sensor that basically counts the number of people that are going in, plus we have our camera sensors, right? So with that, it allowed us to even actually look at, as when the COVID started, right, how the trends of the ridership changed. So we actually have some information from basically Chattanooga and Nashville. And then we have some information on basically how the COVID cases were rising and sort of what was the big change in the transit patterns. So the point was we were able to very accurately start predicting what will be the demand on any particular day. Even under COVID, we were able to guess that, right? And now we are seeing that the demand is, by the way, coming back, because as people are becoming more relaxed and people are getting used to things, demand is shooting back. We were able to actually do few things demographics wise. We were trying to actually understand how this whole demand model, how the COVID-19, the transit demand has impacted different people. So we were able to do correlation, right? So a lot of things, we saw that the biggest effect were people with low income housing. And it's not surprising, right? Because people with low income housing are the ones who are actually using transit more, and they were impacted more. That's where the demand basically fell down a lot. And they had to actually suffer. So we provided all of this back to the transit agency. But where this becomes a part of the optimization, because now we know what the demand is going to be. So that's how we can do the frequency and the assignment. Let me talk a little bit about the energy analysis, right? So all the data that we are collecting, and again, here's a paper. If somebody is interested, you can actually read through this paper. All the data that we have collected, we can now actually take a look at the bus route on the y-axis and the kilowatt hour per mile. And we converted the diesel's kilowatt hour per mile also, and we have electric. So you can already see kilowatt hour per mile of electrics is lower than the diesel, right? So this was always the promise that the electric vehicles are more efficient, and we are seeing this in the data now, okay? We can actually see how things are changing. What we can also do is actually try to do a correlation with the kilowatt hour per mile for each of the different kind of buses across various covariates. So JF is jam factor. Jam factor is how much congestion is on the road, right? So you can see for example, as the jam factor increases, the kilowatt per hour per mile will increase, right? So that means efficiency is getting decreased. So if the buses hit traffic jams, they get more inefficient, right? Not surprising, correct? Because you will brake and speed. Now here's the good news. If you look at this correlation, which one do you see the lowest? BYD. This is our electric vehicles. So this should start giving you a hint that what is all this optimization about. Now, if we can predict that there is a certain route which will actually have a lot of traffic jams, which bus is better to use? Electric bus. Okay. On a road where you will actually have free flow speed, run the diesel bus, move them there. Okay. So you will get more impact of electric vehicle when you use them on roads with heavy traffic congestion. Basically, diesels will suffer much more with traffic congestion than electrics. And we can do this for a number of things. We can do this for temperature, right? Now, of course, this should also not be a surprising guess, right? So as the temperature decreases, right, there is a negative correlation, basically, right? Negative correlation means if the temperature decrease, kilowatt hours per mile of electric vehicles will increase. So if it is getting really cold, you better not use electric vehicles too much, because they will be much more less efficient, right? So on days you may actually on those days you can now compare with the data that just run the diesel vehicles, because that is still more energy efficient, right? And they have hybrid vehicles as well. Okay, we also found things with humidity, and APC events are basically number of stops and count. So the more stops you have, now this is a slight outlier. We can't explain what's going on here. But in general, you can see electric vehicles are easier to stop and go. And this is basically the same as stop and go in the jam factor, right? So just this data itself actually can provide insights into under what consideration should you use what kind of vehicle. Okay. And I'll skip this. This is basically the same thing. We have actually created some dashboards for our partners, and we have given this to them. Okay, so this basically we have been collecting for 3 years. All the data has been collected. We can actually present this information. We have given this information to Department of Energy. We have given this information to CARTA, and now they can start using this. So now we can actually work on energy optimization. So the basic thing of energy optimization is solving this puzzle on the top. So you have number of trips. You have to assign a vehicle to a block, a trip, and you not only need to assign it, you also need to know when to charge it. Let's say we are solving it just for the electric vehicle. When should the electric vehicles should charge? Now, in order to do this, we basically need two things. We need actually energy prediction of if I do assign it to this particular route at 5 a.m. or 5 p.m., what will be the energy consumption? So that's why you need some machine learning, some artificial intelligence, and all the data that we collected before, it learns from the data and starts predicting the values. Okay, and then you can solve this big puzzle of charging. So how do we solve this puzzle? So we actually create a model, right? We understand what are the different kind of vehicles we have. So ICE means internal combustion engine vehicles. Electric vehicles, ignore the mathematics. Every vehicle has battery capacity. They need to charge. These vehicles can serve throughout the day, and you have different trips, right? Each trip has a route, an origin, destination, start time, end time. Route has the fixed direction, fixed road, so you know the road elevation. We have already collected the data. By the time you can predict the traffic, you know how the traffic will impact, you know the stops. You have the demand model, so you know how many times it will stop at a particular stop. So now you can, with these two things, you can actually predict what will be the energy consumption. Okay, now when we do this, we also try to understand what is the time when the vehicle can actually be charged. So we divide the time into specific days and then present some time on fixed charging slots. You have a charger that when can the vehicle charge, right? So now you have two problems. If you assign an electric vehicle to a route, you also need to make sure that the charging is free. So when the electric vehicle finishes its run, it can charge. And you need to know how long does it take to charge. Now we have all this data, right? With this, we can actually start creating basically a model. And in this model, the way it works is we take each trip, right? We assign it to one bus, and then for that bus, when it finishes the trip, we do the charging slot, right? So you can actually do this in a combinatorial way by taking all the possible combinations in the day and just run through them, okay, and evaluate everything. And then finally, because you have predictive models, you can come up with the final answer and say, here is the possibility that these are the set of assignments and charging times that are best. But unfortunately, this is combinatorial. This really, really blows up very quickly when you do all of this optimization. And in real world, anytime you do this kind of linear optimization, linear programs, it will cost you. It will take a long time. So basically what we have to do in this case is minimize the energy cost. For this is an equation that says gas vehicle, and this is the estimation of energy of using that assignment on a particular road. This is the set of electric vehicles. Look, we are not just trying to optimize the electric, we optimize it in totality, the total cost of the system, the energy cost, okay? And that's where our neural networks come in. So I'm going to just quickly show you some designs of the neural networks, right? I don't know if you are familiar with the ML, but just you can try to understand one basic thing. When we train neural networks, we do not train a neural network for each kind of bus route and by combination of electric vehicles. We actually have a single neural network that knows to speak electric vehicle. It also knows to speak diesel vehicle, and it spits out for each route segment. So every time you ask it a question, it can actually tell you some answer on a particular road for each kind of vehicle. And you tell it the time, you tell it basically what the vehicle speed will be, what is the weather at that time, that road segment, what it looks like. And we have one of these models for each segment. So there are around 3,000 segments, stop to stop, for the whole city. And so we have these 3,000 networks, and we run it, and whenever we want, we can ask them a question and they tell us the answer, okay? We also did train some of the other models. Typically, people train linear regressions as the first possibility of prediction models. Sometimes they do random forest. We trained everything, and we know our artificial neural networks actually work the best. These are our models right now are state of the art in this. Okay. And we have seen that, which of the covariates really affect the prediction the most. So weather is obviously the one that affects the most, and traffic affects the most, basically, right? Now, just very quickly, we also have the capacity. So the first models that I showed you, they go at the route segment level. So they can talk about the whole route, that if you start at this time, what will be the energy at the end of time. We also have the capability, a second class of neural network models that we call microscopic neural network models that tell you in a second. They track the bus as it moves. Every next second, they can actually tell the driver what they should do. And this is what we call microscopic. So it gives us trajectory level information of the energy usage. So at what point the energy usage will increase, what point the energy usage will decrease. Now, why you do this? Because this actually then allows you to try to estimate how to change a particular driver's driving behavior. We haven't done that yet. This is something we are still building, but that's the idea. Later on, we can actually give driver suggestions. Hey, you should be driving a little bit more gently in this area, and that can increase the energy efficiency. Now, in these microscopic models, one of the things is the longer the trip, the better the model becomes. The shorter the trip, the more error is there in the system, the models that has been learned. And this is understandable because the more the model gets time to adjust. So for very short trips, the model have error, but as it observes the driver driving, it learns and it can start reducing the error of the prediction. Now, this is already something that we can actually use to provide the driver a continuous feedback of how the driver is doing compared to the expectation of how they should be doing based upon some other driver's profile who has been driving gently. So we have been building comparison map. So try to get the most gentle drivers, their energy profiles, and then show it to the drivers after the trip. Look, there's a big difference between how you did and how this was done. And our plan is to be able to train the drivers to be a little bit more gentle on the runs. Finally, when we put all of this together, right? And remember, I told you that when we are actually predicting and when we have to do this assignment, it's a very hard problem. So we use simulated annealing to solve this. It's a way to actually do the heuristic approximation. If you follow this link, there is actually a Docker engine and Docker image where you can actually run this whole thing by yourself every step of the way. It actually runs for Chattanooga. For another city, it will take much bigger things to try to transfer. But for Chattanooga, it runs because that's where we collected our data from. We can actually already show that from regular, and we have two solutions. One is greedy, one is simulated annealing. With simulated annealing, we can actually reduce up to 5%. This only reduces up to 3%. But we can basically daily start saving around 400 costs and annually around 140,000. By the way, this is the best thing. Saving energy also translates into saving money for the agency. So doing good is actually good for them. So you get rid of a lot of CO2 emission, but you also actually save them operational money. And that's what we have shown them. And basically we are working on integrating this into their system. Okay. Now, our overall long-term goal with them is to actually get a 10% reduction in total energy costs. Okay. If you see right now, we can reach 5% just by doing strategic assignment. We want another 5%. That's how we have challenged ourselves. Now, in order to do that another 5%, what we really now need to look at it is basically how many people are being moved. We need to move more people. Plus, we may need smaller buses for some areas. So we are actually working with paratransit vehicles and microtransit vehicles in some areas to move and then bring that to the table. And for that, we are actually building a complete system, a cloud system for Carta, where all of these things, so you can imagine now it's a cloud system that's giving continuous assignment. It's actually will tell the people, the commuters where the buses are. For some regions, it will actually send them on-demand vehicles. It will allow them to carpool. And overall, at the holistic side, it will continuously monitor what is the total efficiency number of the system. Because at the end of the day, while it wants to meet the service rates, it wants to lower down the energy costs. So thank you very much. That's the work that we have till now. And I can answer any questions.
Thank you. This is very interesting in terms of all the overall design. Any questions?
Have you been able to test the accuracy of the predictions?
Yes, actually, Eleanor, yes. We tested this directly on the real data because again, remember the sensors are coming anyway. So in our papers, we have actually reported our models are fairly accurate compared to state of the art, right? I cannot quote you the number right now. I don't have it on me, but we have tested them with the real telemetry. And this is the most important thing. A lot of people from the past who have tried to do this, they do this with simulated data. We don't need to. We have the luxury of real data because of the sensors. So we do the typical thing, training, hold out. We predict for some day and then we observe that day what happened.
Thank you.
So, Dr. Dubey, what kind of cameras and where do you put it on the? Is it on the box?
Yes. Okay. So as far as the camera work, I didn't go into too much detail there because the camera work is it's not that interesting. It's basically simple machine learning. What we do is we work with the cameras that are directly on the buses themselves, right? So our partners in University of Houston, they do a lot of this camera work, right? And what we can do with them is just take a look at the cameras that are already in the vehicle. So for the security purpose, they already deploy them. So everybody who's going in a bus, and I'm very sure in Nashville this exists, in Knoxville it must, it's because every bus has a security camera. They're already observing it. So then you can start using that for the analysis.
So it's not on the passengers.
It is on the passengers because it is the security camera. So almost all the buses have security camera that observes the passengers. And this data is going to a control center, because what if a passenger is disruptive, right? So the usage of these cameras was always, the role was for security, for operational efficiency. So try to make sure that there is nothing happening that should not happen.
Okay.
But
I was thinking about privacy with people.
So this is where, look, when people are actually going on the bus, this data is not public. So the data that we have, we don't share. But just as when you go into any public space, there is a sign that says you are being monitored. At that point, you have a choice to get down the bus. You know you are being monitored. If you get into a public bus in public area anywhere with a camera, you are being monitored. So you know that, and you have a choice to get down. But I know we understand that using this data comes with a lot of responsibilities. So we have to go through institutional review boards to try to understand that this data can never release. Actually, if you saw some of the data that I showed you, it has faces are must. We never track faces of people.
I see.
For example, because that will go against our IRB guidelines.
Yeah. We
only count the number of people.
Right.
But frankly, you people, when they go into the bus, you have a sign. You should read. It basically says you are being monitored. If you go to an airport shuttle, it's monitoring you.
I see.
You go to parking space, it's monitoring you.
Mm-hmm. Okay, thank you. Any other questions? I have other questions.
Hi, I have a few questions, if that's okay.
Yes, Jillian, please go ahead.
So out of curiosity, when it comes to sensors and integrating them in the public transit systems, what is the cost effectiveness of providing the sensors in each individual bus, as well as paying for the computing power with the neural network versus integrating more electric vehicles?
Oh, so this is much less. So electric vehicles, Jillian, costs a lot more. And even if you get all the electric vehicles, there will always be, remember, for a long time, in all transit fleets, there will always be backlog of old vehicles. Nobody's selling those vehicles. They still exist, right? So there will still be a big city like Nashville in a month can run around 40,000 to 50,000 trips, right? Each trip is a single vehicle. So you will be using a big fleet. And at that point, you do want to monitor the fleet, what they are doing. So I think sensor is orthogonal to the cost of the vehicle.
Gotcha.
As far as the neural networks, they don't really come with any cost. They are just training costs, right? It's not economic cost. And typically, again, all the major transit companies are running a cloud computing infrastructure or have a partner with a cloud computing company. Because right now, all the operations are data-based, right? So in that sense, I would try to answer your question in a circular way, that I don't think these two things are comparable. The cost of sensor infrastructure is so low that you can put the sensors in all of your vehicles for probably less than the cost of one single electric vehicle. But that's a wrong way to judge it. I think you need to do both. Whenever you can afford the electric bus, you will get it. But the point is, instead of doing it in a non-strategic ad hoc manner, you want to have data that provides insight into the system so that you can do it in a little bit more strategic fashion.
And would you say that by using the sensors as well as your neural network computation, you're able to take in more city data versus just looking at one city or like smaller scale?
No, so we are only, right now, we only operated in a single city. So
Mhm.
all of these are slightly different things, right? So when you build, if you just build the sensor infrastructure is trying to get data from all over the city, and you really cannot have any data-driven procedure. Or people say, let's do AI, right? AI does not start without data. So you will need the data, and you will need to put sensors all over the place. The more data you have, the better AI you can get,
Gotcha.
right?
Yeah.
So our work can actually already handle Nashville data, it can handle Chattanooga data, and then scaling up is just the function of how much money you have, right?
Mhm. Thank you.
Other questions?
Yeah, I have a question. So since this allows some predictive and, like, I guess, optimization for bus routes and whatnot, is the city using this to plan any future expansions of the public transit system?
So not right now. We are actually, Carta is our partner, and we continuously actually assess. There are a lot of things that actually come into the picture when you are trying to talk about future expansion. And some of the things that I didn't even talk about in our conversation today, and those are more social criteria. So for example, what is the demographic? Is it a minority area? Do you provide equitable access or not? Are you fair in providing the allocation? So it's not only the everything that I showed you today works through numbers. It just works through what's the budget, and that's it. Let's optimize. But when you try to extend the things, at that point you have lots of other consideration. So they have all the information, and we work with them. But at that point, when they are extending, they bring local planners, community observers, community organizers, and they have to go through a lot of things that are more than this to try to extend. Operationally, things are slightly different. So once you fix the region, right? So we get out of extending new routes. Given the set of routes, what is the best you can get out of?
Yeah.
Right. That is what we do. So we don't change the trip schedule. We do not change the trip frequency, because that, assuming you have worked with the community, make sure everything is equitable, everything is fair, and then you came up with the numbers. Now we say, okay, so you decided you're going to do this. What is the best we can do for you? Okay, that is because you have to be very careful. If we just go with the technology lens, you may end up in a solution that is unfair to some people.
Yes.
And we have to be at a city level, you can't do that. You have to make sure that is not done in that way. So that's why we work on operational side, but the long-term planning, they have lots of other considerations, but we help them as they ask.
Okay.
I have a question. And this is pretty broad. I know you're mostly looking at sort of this traditional mass transit, but I'm wondering what you think of for the sort of the future of transportation in cities, right? And we start thinking about all the mobility things that are out there, whether it's scooters or e-bikes, and we could talk about autonomous vehicles, but like I was intrigued by this because of one of your initial slides about showing ridership versus coverage, and that, I mean, how it seems like you've got a pretty large optimization problem there, but the actual thing of mobility for a city is even much larger. Do you just, I know there's not a real specific question there, just sort of wonder what the future of transportation in cities is.
I understand the question, and as you can understand, there is no answer. But we do, how about this? We understand the problems. So the problems are that this is a multimodal transportation system. There is no central supervisor, no central operator, right? Every car driver in the city is free on its own. They have free will. They will do what they want, right? You can run a car share program. You can have electric vehicles. You can actually have the scooters. You can have e-bikes. You can have bikes. But at the end of the day, you can provide all the choices. Then it's really the rest of the population that actually uses the choice. And there are almost all the cities, if you look, they run these days something called transportation demand programs. Nashville runs it. Chattanooga runs one. I am not familiar with Knoxville's case, but I'm very sure there is a program that Knoxville also runs. The question there is like, because look, we cannot really make somebody do something, but this was a question that came, people are not using transit. So what kind of carrot can you really give so that people start using? And this is where the incentivization and at that point, it becomes more of a game theory problem and economics problem, and you design the right set of levers so that people can start making the change. And what I think will happen is slowly and slowly, cities are realizing that they need to do this with multimodal things, and they are making some changes. So for example, this whole mobility of bikes and scooters came in. Rideshare was supposed to be a panacea. Everybody thought that Uber and Lyft will get rid of the car problem. But now that the data is coming out, people have started realizing, hey, it's not always true. Sometimes car share is actually increasing traffic in some cities. There have been studies from New York and others, if you see, because the drivers are then circling around trying to find people. So this is a very dynamic problem. No solution exists. And this is where it's really, I think, not necessarily just a technical problem. This is a massive problem with trying to work with people. And you will have to actually work with trying to figure out the right set of incentives. Now, here's the silver lining in pandemic, Kevin, right? So what the data shows us, again, we can look at the traffic congestion values, and you have probably seen a lot of these studies all over the place, that the traffic patterns have sort of changed from 2019, right? So what that is telling us is that people are preferring to do things like what we are doing right now. We're talking on Zoom, working from home. So when you're working from home, talking on Zoom, you're not really traveling, right? And in that sense, the number of single vehicle trips are probably reducing. Now, whether it will remain like this or not, I don't know, and nobody knows. But maybe this has been a silver lining, right? That we have actually managed to achieve lowering of the number of trips and improving the things that we want to do for the climate just because of this. Now the question will be, how can you sustain this?
Thank you.
Well, I think extended what you're just saying, the related policy, I think this electric vehicle buses is mostly, I think mostly benefit to low income areas. So did you see already the city, Chattanooga and also Nashville have already planned in like going to the low income areas?
Yeah, so again, I cannot speak for them, but I know they have programs. So they have their guidelines from Federal Transit Authority that they have to follow in how they define accessibility, how they define equity, and they both follow this. So for example, they cannot also just say electric vehicles will be concentrated in one area and not in the other area. They try to distribute, and there are people there who specifically whose job is to make sure things are fair and things are done in a way which the guidelines say. And that's why they also run a number of services called paratransit services. So for people who cannot access the buses by themselves because of a number of challenges that they can have, physical challenges, they can be served by these on-demand trips. So vehicle goes to them, they pick them up, and then they are dropped to their location. So there are programs like that already. So when we look at holistically, that's why the problem becomes very, very complex. And that's why it's a social technical problem. We can come from a lot of side on the technical side, but you really have to study the social side as well. In our team, we have people from Peabody, people from University of Tennessee, Chattanooga, who are just looking at this social community problem and trying to understand everything that we are doing. Are we doing it in a proper way or not?
Great, thank you. Any other questions?
I've got another question, if that's okay. When it comes to the bus stops, have you given any thought to monitoring or providing sensors for the individual stops that the buses are taking? Like, for example, if a bus was supposed to stop at a bus stop, but there's no individuals present, like skipping that stop if no one's planning to get off there to improve efficiency. And then also, secondary question to that would be, if a driver is notified of an optimal time to go to charge, do they abandon their route and then another bus takes that up? How does that work?
Okay, so let me answer the second question. No, that cannot happen. A driver can never abandon the route. So it's part of our constraint problem. We can never tell a vehicle to charge until it finishes its trip. And that's why you need to understand before allocating a vehicle to the trip that it has enough charge to run the whole thing. Okay.
Mhm.
So it can never happen. that will be that will be a wrong answer completely.
Okay.
The second thing is of the first question that you asked about stops. So we don't really need a sensor at the stop. So we actually every bus in almost every city already, including Knoxville, including Nashville, and every other major place, actually have something called automated vehicle locators. These are GPS sensors. They are continuously monitoring the vehicle position, and they know, everybody knows precisely where the vehicle is and if it is at a stop or not. And you also know that the vehicle is stopped at a stop and it's moving. So you can imagine now we can take the automated vehicle location, we can take the telemetry, and we join them together. It's a massive join, big data join, but it tells us, oh, what was the vehicle location, how many people got into each stop. Now, as to whether you can skip a stop or not, that really depends on the policy of the transit company and the operator. Most of the time you don't, because it's a contract. You promise to people that you will stop, but sometimes if it is really required that there is nobody, they will quickly stop and then quickly take off. Okay.
Gotcha. Okay. Thank you.
Yeah.
All right, very interesting research. I have more questions, but we'll discuss later. Yes, great job. Any other questions before we close up today? No? Okay, so let's thank Professor Dubey, and thank you for this very interesting presentation. And I really like your graphs too. You have a very good presentation graph.
Yeah, thank you, Chinfi. Thanks everyone.
All right, thank you. I'll
Bye.
see you next week. Thank you. Bye-bye.
Bye.